Welcome to today's video illustration. Today I'm going to be showcasing a page ranking Python file which ranks each page based on its quote-unquote importance. And the algorithm that this program is following is the page ranking algorithm, which was created by Google's co-founders, including Larry Page, for whom the algorithm was named. And it basically suggests that a page is more important if it is linked by other important websites as well. And so we're going to go on calculating a page rank using two algorithms or two methods. The random surfer model using some sampling algorithms, and iteration using a formula that we'll just describe in just a second here. So in the random surfer, we imagine that we have a bunch of pages like the ones shown here, and the random surfer will start at 1, will start somewhere at random, let's say page 2 for example, and then they will pick now his two options, either to go to page 1 or page 3. So they'll just pick one at random, and we'll keep repeating this process n times, and then we'll see how many times did a certain page appear, or its probability of appearing at any given time, and this will determine the importance of that page. So this way, if it's linked to more pages, it will more likely be visited more times. And now one last thing to put into account here, which is the damping factor. If we take this model, for example, we'll see that if we start at page 5, for example, it will just be a 50% for page 5 and 60 for page 6, since you can only go to page 6 from page 5, and so on from page 6 to page 5. And to solve for this issue, we'll introduce a damping factor. In this case, it will be an 85% chance. But basically speaking, when you're picking between which page to go to, any page, there's a 15% chance that the surfer will pick anyone at random. So if I'm on page 5, there's an 85% chance that I'll pick page 6, and 15% chance that I'll pick one of the 6 pages at random. Likewise, if I'm at page 2, for example, I can either go to page 1 or page 3. There's an 85% chance that I'll either go to 1 or 3 randomly, and a 15% chance that I'll pick one of those 6s. This way, if I'm in a page with no links or just one link, we won't be stuck there, and our algorithm can continue moving on. Lastly is the iteration algorithm, which will use this formula here. So again, using the damping factor, we already said that we can think of the probability of reaching a certain page by two states: either with the whole 15% chance, so d here is the damping factor, so 1 minus d, which is 85%, so is 0.15. So there is a 0.15 or a 15% chance that the server chooses a page at random, and this page is page P. So this is one part of the probability, right? That it just gets chosen at random. The other side, that has a probability of d, or 85% chance, is that the server is on page I and it chooses page P as its link. So the first part here is that there's a 15% chance, or a 1 minus d, that will pick one at random, and then the probability of picking P is 1 over n, where n is the total number of pages. So if I have 5 pages, there's a 15% chance that I will pick one of those 5 pages, which will be 1 over 5 if I want to specifically pick page 8, plus sigma, or the total number of probabilities that we're at page I, and then multiplied by the number of links in I. So to put this into perspective, I'm just saying that there's an 85% chance that the following happens. And then on each iteration, so I'll consider all of the pages that can go to page P, and then I'll say that the probability that I'll end up at page P is equal to the probability that I'm on page I, so PR of I, multiplied by 1 over the total number of links that I can go to. So if I can go to 3 different pages, then obviously going to page P has a probability of 1 over 3. So it's the probability that I'm on I multiplied by the probability that I go to page P. And those are our two formulas that we'll use here. Let's run the code straight away. So if I open my terminal here, let's just run it. So here is a bunch of folders, each containing a bunch of HTML files that have some links. So if I run it on corpus of 0, you see that the program will tell me here, page result from sampling, 10,000 samples. So, and again, we'll start with sampling. We start at one page at random, and then we get the probability distribution from going to this page to the others, given the damping factor. and then we'll just keep on going to one page at random 10,000 times, and then we note how many times did each page appear, and we'll see that page 2, according to this algorithm of sampling, has the highest importance. And if you look at the result by iteration, we'll find that actually the results are almost identical, since those two are different methods, but they should amount to the same output, which is finding which page is important by our logic here. And so from iteration, we iterated through using the formula. We kept running the formula on all of our PUR of P until there was no change of 0.001. So just to put it into perspective, we have our formula here. Let this load for a bit. Yeah, so we have our formula here, and then we used it. The function starts by assigning everything an equal probability. Okay, so PR of I should be the same for all of them, and then it will keep running this formula. It will keep plugging in the numbers. Note that all of those will be different except for PR of I. So in this case, I have 4 of them. So each one will start with a probability of 0.25, and then we'll calculate this where PR of I will be 0.25, and then that will update the output. Let's say my p here is 1.html. It will be updated, and then 2 and 3 and 4 and so on, and then we keep on repeating the process, updating each formula in the process until the changes we get is less than 0.001. Then we can determine that, okay, we're not making a whole lot of improvement in our iteration here on the probability, so we just conclude that that's the final solution. And again, as you can see here, using 2 different methods will still amount to the same exact output almost. Thank you so much for watching. That's all for today, and have a nice day.